was great and it was terrible all at the same time.
Oh,
it was really just a lot of things.
Okay.
Hi, Lily.
10.3.
Where do you mean
I'm recording.
Lily's on the screen.
Go.
Don't you see him?
A little review of what we did last time. Polar coordinates. So polar coordinates, unlike rectangular, which is x, comma, y, right? You have your horizontal and vertical component. Polar coordinates, you have the radius, how far you are from the pole, from the origin, and then you have the angle, so how far are you swung around. We can convert from polar to rectangular, from rectangular to polar. Just remember, like if I would go and solve this triangle, how would I get the x by itself? Oh, okay, so cosine of theta is adjacent or hypotenuse, meaning...
What page are we on?
Yeah.
I'm doing a little review of 9.3 before I go on to where we left off. So this is page 15, top of page 15. I'm just briefly reminding you guys because we need to know this to go on to the next step. So just, break away those cobwebs.
Right, for sure.
All right.
Anti-cobweb.
Yep. So if I do cosine of theta, that's x over r. Okay, solve for x. Guess what? You just take your radius times cosine of theta, that's your x. Your radius times sine of theta, that's y. Use Pythagorean theorem to find the radius, right? So r squared equals x squared plus y squared. How do you find the angle? Okay, so that's just tangent, right? Opposite over adjacent, y over x. Blah, blah, blah. You can find the coordinates, convert. Keep in mind, if you have a negative radius, that's going to mess with your mind, right? It's going to be crazy. You got to add pi onto your theta. If you have a negative radius, it's given to you, you have to add pi onto the theta. That'll screw you up. If you have your radius constant, well, that's literally a circle. If you have theta that's constant, that's just going to be a line. You can change the equation, blah, 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 make circles. If you have r equals something with cosine, it's going to be a circle on the side. If you have r equals something with sine, it's just going to be a circle up above or below. And then I can make parametric equations of polar curves. Since x depends on the radius and cosine, I know the equation for the radius is f of theta times cosine theta, blah, blah, blah. It's parametric. I can find slopes of polar curves. It's literally just like the parametric slopes that we found. Remember we did dy dt over dx dt, and that's how we found dy dx. Woohoo! Well, it's the same thing here. It's just instead of in terms of t, it's in terms of theta. Very similar. All right, so this is where we left off, is area of polar coordinates. So recall from geometry that the area of a sector of a circle is 1/2 r squared theta, where r is the radius and theta is the central angle measured in radians. By replacing theta by the differential d theta, we get the area differential, right? So the change in area is equal to 1/2 radius squared times the change in theta, which is exactly the quantity that we need to integrate to get the area in polar coordinates. OMG. The area of the region between the origin and the curve, as long as your first angle is smaller than your second, right? We're going from alpha to beta, not being crazy. It's just gonna be this integral. I don't know if there's another way to explain it clearer. I think we understand where it comes from.
I mean, you just find the integral of the,
From what angle we're starting at to what angle we're ending at. That's it.
the angle's changing.
Yeah. I'm wanting to find from this angle, which is theta, to this angle, which is beta. It's like this is the change in angle. It's from alpha to beta.
Okay.
Yeah.
And those are the two angles.
Mm-hmm.
Why do we have? Oh,
It's like from A to B. It's just.
It's the area between those angles.
Mm-hmm. Exactly.
So, like, if I had a 30 degree and a 60 degree, it's what's in between the 30 and 60 degrees. So that would
Exactly.
be like another 30 degrees.
Yep. Exactly. All right. Area between polar curves.
Oh. That's right.
All right. So this is the area as theta is changing. If we know area between polar curves, the area of the region between r1 theta and r2 theta, as long as alpha is less than beta, we can rewrite this in terms of outer minus inner. Outer minus inner, yeah. Okay. Some common polar curves. Oh, guess what? Circles. If your radius is constant, it's the same everywhere. It's going to be literally a circle. R equals A sine theta. So here, I could get the equation. I mean, this is not necessary, but I just want to show you how. Multiply both sides by R. Guess what? R squared is equal to A times Y, because R sine theta is Y. A is just this constant. I know R squared is literally X squared plus Y squared equals AY.
Mr. Brett, Louis texted me and said that he's on his way.
That's fine. You can just watch the screencast catch up.
Yeah.
So I was just going to convert it to, like, Cartesian coordinates.
I don't know how you got
But multiply by R on both.
equals X.
R squared?
R squared equals X squared plus Y squared.
Yeah, yeah. And what this turns out doing is like, oh, X squared, change of base, like Y minus 2 squared, or let's say minus A, equals, it'll turn out to be something like this. Honestly, the point that I'm just trying to show you is, oh, look, it's a vertical translation of a circle, where here is now my vertex. It shifted up A units, and the radius is A.
Yeah.
That's what it turns into. Here, guess what? It's the same thing. This is just going to be like x minus A squared plus Y squared equals A, whatever this number is, because your vertex moves over, and then you have your radius. Okay, that was just like this is what you get. Yeah, circles, rose curves. Yay, look at these roses. They look like flowers. There's not really anything I need to tell you about this. Well, let's see. This one. Yeah, this one. An example of this one, just so you know, is like R equals 2 sine of 3 theta. Because if this was R equals 2 sine of theta, it'd be a circle. But since we have like 3 petals, would be 3 theta. If I wanted, let's see. Yeah, I don't know. That's really the only one I want to talk about. Okay. Lemicon curves. I don't even know how to say
Can you
it.
tell me a pencil?
Yes.
You have a pencil.
It's not a very good one.
I don't have anything better. I could do with pen, but that's not as good as a pencil.
Yeah. Okay, and then lemniscate. Looks like infinity. And the spiral of Archimedes. Spiral of Archimedes is actually pretty cool. Okay, and then I think this is the last page of our notes. Find the area of the region in the plane enclosed by the cartioid. R equals 2 times 1 plus cosine theta.
Why do they call it Archimedes? See the guy?
Archimedes? Archimedes?
Yeah.
Oh, should this be Archimedes?
Probably.
Archimedes? Archimedes is the guy, yeah.
Nice. Cool guy. He just literally said, oh, let's take R equal the angle.
Yeah.
Like, whoa, you're cool. I couldn't have done that.
Around.
What else did you do?
So cartioid looks like this guy. But there's like, some of them have specific names. Lemicon curves have specific names. Lemicon with a loop, dimpled lemicon, convex lemicon, or cardioid.
Well, I do not understand that fourth one.
Convex?
Corner.
Huh?
Convex, yeah. What's different about it? It's just a circle.
It's not a perfect circle.
No.
You see how it's not exactly perfect?
No. Looks pretty perfect. That's okay. Oh, I see. It didn't fit through that outline. So
Something like this, like this is the concave. If the convex is literally like, oh, it comes up.
See it. But I don't know if that's because of the graph or that's because like it's actually there.
It's like skinnier in width than it is in height.
On which side? The right side, right?
Yeah.
Like this is not as long as this is. I know, I'll prove it to you. Okay. Rotate this.
Whoa.
It's a little shorter.
Nifty.
It rotated not around the center, so it didn't work.
Oh, okay, I'll delete. Okay, let's keep going. Find the area of the region, the plane enclosed by the cardioid, r equals 2 times 1 plus cosine theta. Okay, so the region in the plane. So I'm only wanting to go enclosed by the cardioid. So what's the angles I'm looking at here? I want to go from alpha to beta, but what's my alpha and beta?
Different things of beta.
Yes, but I start at what?
It didn't tell us.
We just want it to be enclosed by the cardioid. In order to make it close, in order to be enclosed by the cardioid, I start at 0.
And then you end at 0.
And I end at 2 pi.
Ah. Yes.
Yes.
Very good.
So that is the total angle I'm gonna go through. So the area is gonna be,
0 to 2 pi.
because that's the amount of angles it takes to go a full.
And then it goes around again.
Because I don't need it to go around just twice. I only need to go around once to draw out the full cardioid.
Merry-go-round.
Right. So I just want to go around once. That way it draws out the whole thing, and then I'll find the area. If I only go around half, well, it's not gonna be the full. If I go around 5 times, it's still the same area. But like, why? Only go around once. So area is 1/2. Ooh, going from alpha 0 to beta 2 pi.
How do you know it's 1?
It's the equation from the page.
Derived earlier.
1/2 r squared d theta. 1/2. Sorry, area is 1/2 r squared d theta. That's d area. So if I integrate both sides, I get a is equal to 1/2 r squared. So my r is 2 times 1 plus cosine theta squared d theta.
So that's the square.
You have to square that, yeah.
Wow.
If you plug this into your calculator,
Oh, really? Cool. But like,
I don't have
isn't
my
it supposed to be r squared subscript 2 minus r squared subscript 1?
so that's if I'm
Oh, who's my calculator?
so that's if I have like 2 different items and I'm trying to find the area between them. Versus here, I'm just wanting to find the area like inside the cardioid. The next example is the R1 minus R2.
Nice. Are we gonna have more practice with a problem like that?
Yeah, I'll have more practice because it's hard.
It's just like,
It's just
I
new.
don't think I got the concept. It's
Okay.
easy to just memorize the equation.
Yeah. All right. Let's try number 8. Find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. Okay, so first, do we have any idea what this is going to look like?
Oh, so these are gonna be two circles and a little lima beam outside the circle. So the circle's gonna be totally
Yeah, it's like a lima bean.
That's gonna be my wall.
Yeah, so this is the cardioid, and then the circle r equals 1. Okay. So it's going to look like hey, I got it almost. There's the circle r equals 1. And the part we're looking for this is the part we're looking for.
Oh wow.
Okay, so first let's find the intersections. Because of course my drawing, I'm not an artiste when I draw. Maybe when I bake, but not when I draw. So we gotta find the intersection. So when is the radius, when is the circle, when does the circle touch the cardioid?
Does it touch at the y-axis?
That's what I'm trying to find out.
Both sides? That would be really nice.
Let's see, so I know the circle's radius is always going to equal 1. The cardioid is 1 minus cosine theta.
Oh, so we're going to set them equal to each other?
Yep, because I want to find where they are equal. Where are they the same?
Negative cosine.
Divide by -1, multiply -1, whatever, 0 equals cosine, where 0 cosine. Theta is equal to pi over 2 and 3 pi over 2. So, surprise, I drew it correctly.
So, yeah.
Right here and right here. Cool. So, okay. Meaning, I can go from like negative pi over 2 to pi over 2, right? I just need those two quadrants. I don't want the left two quadrants, I just want the right two quadrants. If I go from like pi over 2, I want negative pi over 2 to pi over 2, yeah. Yeah. Because that way, and then I can take the outer minus inner. And that's how to get the area in between them. So the area between curves. So the first problem we did was we want the area of like our sector, right, with the cardioid. Here I'm trying to find the area between the polar curves. So since I want between the curve, I want between the circle and the cardioid. I'll take the area of the circle and minus the area of the cardioid. More or less, that's what we're going to do. So here, I'm going to do, once again, we're going to use like area equals 1/2 r squared d theta. Okay. So the area is equal to 1/2. I'm going to go from negative pi over 2 to pi over 2. That way it's going like this way. It's going around that way. Okay. So I want the R2, which is the outer, squared. So that's going to be 1 squared. Minus the radius of the inner, which is 1 minus cosine theta squared. D theta. Yep. Is your calculator? Did you have yours, Bradley?
My friend hasn't and he's bringing it right now. Like he's on his way.
Like your friend Louis?
No.
Oh.
That's not you like 45 minutes. We haven't got back.
Why do you do this?
I'm nice. What can I say?
You gotta be, you gotta,
Calculators are very convenient.
you gotta look out for number one, Bradley.
I think in
All right.
Brad's case, though, 'cause you
So
can-
that's it for the lesson.